So our next speaker is Stephen Austin. He's with TxDOT. Stephen is the Field Operations Section Director at the TxDOT Bridge Division, where he directs statewide support in the areas of bridge inspection, bridge preservation, construction, maintenance, and geotechnical engineering.
One thing on surveys, it was mentioned a second ago, we're going to have a survey out on bridge decks, repair materials. Please keep your eyes out for those, for that survey that's coming out probably in another couple of weeks or so. But getting straight to the presentation, I'll be discussing our experiences with concrete metalizing on the Queen Isabella Causeway. I'll start off with a brief overview of what concrete metalizing is. Most of you all probably are familiar with what concrete metalizing is, but I'll give a brief introduction to that. I'll talk about the significance of the Queen Isabella Causeway. I'll go over the history of concrete metalizing on the Queen. We call her the Queen in Texas. And then I'll talk about a more recent condition survey for bridge preservation. We do condition surveys prior to any major rehabilitation or preservation effort at TxDOT. This is a major bridge in Texas. We conducted we had a condition survey done on this bridge. And then I'll close with some summary of findings and our path forward. So what is concrete metalizing? It's the application of a metallic material, usually thermal sprayed aluminum or thermal sprayed zinc, to provide some cathodic protection to prevent corrosion of reinforcing steel. It's usually applied in salt-rich environments, so you'll see it used a lot in coastal states. FHW research has shown that this metallic coating can outperform many other coatings. It provides not only corrosion resistance, but it provides resistance, durability against abrasion, and the eventual, it provides a barrier to resist intrusion of chlorides. Some sources suggest upwards of 25 years of life for a metallized coating. In a marine environment, however, the life expectancy is going to be significantly reduced, and you'll see that from the presentation. By the end of the presentation, you'll see what I'm talking about. Metallizing can be effective with an impressed current or passive system. Impressed current is basically the exact same system, except it's got a power source that helps the flow of the electrochemical reaction to occur. This is a quick drawing to illustrate the corrosion process. What's shown here is a reinforced concrete section, and at the very top you see the drop of water. That represents salt water coming into a concrete surface. It starts to, first, electrochemical process of corrosion starts off at the anodic site. The chlorides mix with iron, and the byproduct is electrons. So electrons flow through the connectivity of the reinforcing. We might have ties tying reinforcing together, or we might have rebar just touching. But this allows the electrons to flow from the anodic site to the cathodic site. Once the electrons are in the cathodic site, that mixes with moisture to produce hydroxyl ions. So that travels back to complete the circuit, the electrochemical circuit, back to the anodic site, where the hydroxyl ions mix back with iron with the iron in the steel to produce the corrosion. We can we can disrupt this process by introducing a more electronegative material. So zinc is frequently used, and aluminum is used as well. Zinc is more electronegative than aluminum, so you'll see it performs better. But the most important part in this process is that there's a connection between the once anodic steel and the newer zinc material. And so this zinc material is usually called an anode or a bulk anode when there's a mass of zinc used as part of the cathodic protection. When we're metallizing something, we'll completely encase a concrete element or cover the concrete element largely in this metal surface. So effectively making the anode the coating. So the metallic coating becomes the anode. And rather than the reinforcing steel starting to corrode, what's now going away, what's now getting consumed is the zinc material. So now that we know what concrete metallizing is, let's go back to Texas. Our Queen Isabella Causeway provides the one and only access from Port Isabel to South Padre Island. So South Padre Island is in the southern southeast tip of Texas, and it's highly corrosive environment. South Padre Island only has about 5,000 residents or so, but each year upwards of 5 million visitors flock to South Padre Island, especially around the summer. So it's a real critical bridge for Texas. The bridge is about 2.5 miles long. It was built in 1974. It consists of 150 spans. 3 of them are steel plate girders, and over the main navigable waterway are 147 spans are pre-stressed concrete spans. The bridge carries 2 lanes each way and has an overall width of about 68 feet. And the bridge has had several preservation projects. Cathodic protection is one of them, but it's had joint repairs. We've had deck repairs, beam end repairs, and steel painting. The bridge has also had its share of bad luck. It was hit by an airplane, and it was hit by a large barge that took out a couple of spans, not at the same time. So now let's go to history of concrete metalizing on the Queen Isabella Causeway. In 1996, there was a demonstration project, was intended to evaluate different cathodic protection options. Of these, thermal sprayed zinc with both impressed current and passive coating was utilized. Then they used thermal sprayed titanium, and then a titanium mesh concrete overlay. Prior to the installation and determining that this bridge was appropriate, bridge assessment was done. There were cover meter readings that indicated over 3.5 inches of cover. The crack widths were varied, but no significant crack widths were found, and there were surprisingly no delaminations identified. And I say surprisingly because here in this next slide, you'll see that there was chloride samples taken that measured upwards of 20 pounds per cubic yard. The commonly accepted threshold for corrosion for unreinforced steel is about 1 to 1.5 pounds per cubic yard. So we're talking about significant chloride contamination already. Granted, this may have been at a crack, which maybe skewed the numbers a little bit, but there was a lot of chloride. And it makes sense. This is in a saltwater environment. Half-cell potential readings were also taken, and they correlated well with the cracks. This demonstration project focused on the portion of the columns, the lower portion of the columns, 2 feet of the columns, and the footings, as well as tie beams. And I'll show pictures of that in a minute. But key findings of the project were that the titanium mesh and the titanium sprayed protection performed worst up front. They had premature deterioration. So this again was the most costly product that wasn't performing very well. Sprayed zinc provided the highest productivity of installation, and by the end of the demonstration project, it showed that it performed best of all of the options. Then aluminum. So in 2004, after we took this demonstration project results, we led a project in 2004 and then a subsequent one in 2005 to install metalizing on all of the bents. In 2004, 72 bents were zinc coated and 14 bents were coated with an aluminum alloy. And then in 2005, I think we just dug a little deeper into our wallets, into our purses, and came up with the rest of the money to do the remainder of the 57 bents on pile caps. So you'll see in this picture, you can make out that the footings and the tie beams and just 2 feet of the column were coated were metalized. The end bents, about 7 bents on one end and about 10 bents on the other end, were not of the same substructure type. These were more trestle pile bents, so a series of piles rather than a pile cap or a footing and 3 columns. These end bents were treated with jackets and then bulk anodes. And this is important. Keep this in mind because we come back to looking at the performance of these later on. After being in service for 4 to 5 years, depending on which project we're talking about, we had an assessment performed. This is in 2009. We had an assessment performed to evaluate the effectiveness of the coating. Conclusions were that the cathodic protection, the metalizing, was performing quite well. and there was more rapid consumption of the aluminum alloy than there was the zinc coating, so the zinc coating was performing well. The recommendations from the 2009 assessment were that we should recoat the aluminum, remove the aluminum coating, and then recoat with zinc coating. One problem with the zinc coating was that there was more rapid consumption at the connection to the reinforcing steel. This, like I mentioned up front early on when I was going over the discussion of what metalizing is and cathodic protection, this connection to the reinforcing steel is critical. Without this, it renders the metalizing pretty much useless. So 5 years after installation, aside from the connection to the reinforcing steel, the connection plates needing to be replaced, there was an estimate that the metalizing could be in service for another 5 to 10 years on the zinc, on the zinc applied coatings. So in 2011, we went back and we replaced the aluminum alloy with zinc coating, and then we installed new anode connector plates to nearly all the locations. So fast forward 7 years beyond that, and we're ready to do a preservation project. We see that there's a significant loss of metalizing coating. We plan on looking at the bridge again. So we look at the bridge again and found that the 2004 to 2005 metalizing is pretty much completely consumed. There are many locations that it's completely lost. Thermal sprayed zinc that was applied in 2011 looks like it's blistering about twice as much as the 2004, 2005. So this kind of tells us that the second application is problematic. And this is problematic because during the recoat, you want to remove the existing surface in its entirety because you want to make sure that you've got a good contact to the concrete so that the moisture is allowed to move and the electrochemical process, the circuit, is able to work as intended. Half of the 2004-2005 bents tested showed ineffective cathodic protection based on polarization testing and half cell potential. So we're at the end of the useful life. So the 2004-2005 got us to 2018 pretty much. 2018 recommendations were reapply metalizing to all of the bents, and this comes at a cost of $9.5 million, and we might get a service life of about 20 years or so. We wanted to take a closer look at this. A couple of folks in-house take a look at this bridges one more time. We saw that after 7 years, the anode connection plates needed to be replaced, and then after 7 years of the reapplication, that was the end of the useful life was approaching. So we went out there, took some resistivity meters, and the resistivity readers indicated that there was active corrosion, that we've got a problem that needs to be addressed. The 2011 application was also approaching the end of its useful life. Some top of footings readings were in the single digits even. Very low resistivity means that we've got active corrosion. At the same time, we used this as an opportunity to look back at the bulk anodes and the jackets that were installed back in 2004. And the cathodic protection that we found at these bents appeared to be performing really well and continuing to be effective into the bent caps. So we've got these bulk zinc anodes that appear to be working really well. In summary, the performance of thermal sprayed zinc and thermal sprayed aluminum is not as effective as anticipated, likely due to the splash zones contributing to quicker consumption of the metal coating. Life expectancy of thermal sprayed zinc is greater than thermal sprayed aluminum, and a 15-year life may be achieved, but in the case of the Queen Isabella Causeway, it's for the first application, and we required replacement of the connection plates. Every 7 years, it seems like we're doing maintenance on these. To address poor construction quality issues in splash environments, we think the GFRP jackets with buried zinc anodes in lieu of concrete metalizing would work. Now, GFRP is not necessarily a good application on these large footings. Instead, we did some research and contacted folks in Florida, and it sounds like what they've got is a system where they're pretty much using bulk zinc anodes without without performing thermal sprayed zinc, thermal sprayed aluminum, and they're getting really effective results. Our plan is to do something very similar to this, to install submerged zinc bulk anodes and tie them to existing reinforcing in the footings in the pile caps. We think that this will give us about 7 to 10 years of life, and we estimate, depending on the size of the bulk anode, but we estimate that this is going to be costing on the order of $3 million for installation and monitoring. We want to make sure that we monitor this because this is something that we haven't done very much of without thermal sprayed zinc, but we're confident that we'll be in real good shape. So stay tuned because we're going to end up moving forward with at least a portion of the bents with this repair method. So if there's any questions, I think I'm out of time, but I can probably entertain one. We did, we actually had, as part of the assessment, the $9.5 million was the passive system. I think the impressed current added another $3 or $4 million on top of that.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.